All right, we're going to begin using the equilibrium constant expression to try to find things out about various chemical reactions. So let's say we're looking at this particular chemical reaction where hydrogen gas reacts with iodine gas to form 2 moles of hydrogen iodide in the gas phase. And let's suppose we start with 0.0175 molar of hydrogen gas and 0.0175 molar of iodine gas in a flask, and there's none of this present. And then we know that at equilibrium, so when the system comes to rest, we're able to measure the amount of iodine that's left over, and that's going to be 0.0037 molar. With this information, we should be able to find the value, the numerical value of the equilibrium constant. Now, the way we're going to organize our thoughts is we're going to keep track of the initial conditions, which I've stated here with an I. So the initial conditions are 0.0175 molar of both hydrogen gas and iodine gas, and no hydrogen iodide. We're going to keep track of any change that occurs in the system as it goes from the initial conditions to down here, which are the equilibrium conditions. And in order to figure out what the equilibrium constant is, we're going to need to fill in this entire row, because the equilibrium constant is calculated by taking the HI concentration squared at equilibrium and dividing that by the hydrogen gas concentration at equilibrium and the iodine gas concentration at equilibrium. So please note that the equilibrium constant is always calculated using equilibrium values of the reactants and products, of course raised to their appropriate stoichiometric powers. So if this is true, if this is the information given, how can we find the numerical value of the equilibrium constant? What we can do is we can certainly find the change that's occurred in order to go from 0.0175 molar iodine to 0.0037 molar iodine. So, this difference will tell us how much of a change occurred. So if I take 0.0175 molar iodine and I subtract 0.0037, we know that the iodine must have lost 0.0138 molar, right? Because 0.0175 minus 0.0138 is 0.0037. And by stoichiometry, for every one of these that reacts, one of these must react. And again, it's the case where 0.0138 molar of hydrogen must have been lost for equal stoichiometry. And of course, we have 0.0037 molar for our equilibrium value of hydrogen. Now, the amount of change in the hydrogen iodide is going to be twice this, right? Because for every one of these that reacts away, 2 of these will be produced. So the change that's going to happen is twice this. So we're going to say 0.0138 times 2. We're going to have a positive 0.0276 in the HI. Remember, twice the amount of this will form as the amount of this that decays away. 0 plus this tells me at equilibrium I'm going to have 0.0276 molar of the hydrogen iodide. So the value of the equilibrium constant then is going to be this value squared, the equilibrium value squared of hydrogen iodide. We'll also need to divide by the equilibrium concentration of hydrogen gas and also the equilibrium concentration of iodine. And then when we calculate this value, we will have the value for the equilibrium constant. So take 0.0276, multiply it by 0.0276 to get this squared. We'll divide by 0.0037 for that one. And we'll also divide by 0.0037 once again. And the value of the equilibrium constant for this particular reaction would be 55.6. Now we can use this value of the equilibrium constant for this reaction and any conditions that were given initially to figure out which way the reaction is going to go. Let's show you how this works. So let's take hydrogen gas, this is our reaction, plus iodine gas, reversibly going to 2 moles of hydrogen iodide gas. We know that our value for the equilibrium constant, which is going to be the concentration of HI squared over the concentration of hydrogen gas and also over the concentration of iodine gas at equilibrium, which is when the system's at rest, so to speak, should be 55.6. And let's assume that we have the conditions where the concentration of hydrogen is 0.013 molar. The concentration of iodine is going to be 0.056 molar. And the concentration of HI is going to be 0.031 molar. The question is, if this is our condition, so this is my initial condition of hydrogen, iodine, and HI, is this system at equilibrium? Well, that's easy to find. I mean, we just plug everything in here. And if this squared over this times this and also divided by this is 55.6, we know we're at equilibrium. Let's just find out where we are. So what we'll do is we'll say, you know, we don't know if we're at equilibrium here, but we're going to calculate this ratio that has the same form as the equilibrium constant expression. But we don't know if this is actually the value of K or not, so we're going to call it Q, just for this quotient. We'll calculate Q, so let's take it here. That's going to be 0.031. We need to square that. We're going to divide that by 0.013. We also need to divide this by 0.056. So let's see where we're at in relation to the equilibrium constant. So I'm going to take 0.031, multiply it by itself. So that's 0.031 squared. We're going to divide this by 0.013. And we're also going to divide this by 0.056. And we see that we're at a value of 1.32. Now 1.32 is certainly less than the equilibrium constant. So we see in this case Q is less than the equilibrium constant. If this is the case, which way will this reaction proceed? Will it proceed in this direction or will it proceed in this direction in order to get us to equilibrium? Well, let's think about this. We need the value of Q to be bigger. That means I need this value to be bigger or this value and this value to be smaller, right? If you divide by a smaller number, you get a bigger number. How does that relate to our equation? Well, if we need the numerator bigger, we need more of this, which means this reaction needs to proceed in this direction to raise our value of Q. Another way to look at it is we could lower the values on the denominator or lower the values of these, which again will occur if the reaction occurs in this direction. So we see for the case that if Q is less than KEQ, than the equilibrium constant, the reaction must proceed toward the products, proceed toward the products to reach equilibrium. Then, of course, the converse will be true, correct? If Q is greater than KEQ, say we had a value of 1,000, well, then that would mean this needs to be lower and these need to be greater. And that occurs if you head in this direction. So if Q is greater than KEQ, we're going to see that the reaction must proceed in the reverse direction in order to reach equilibrium. And then finally, if K is equal to KEQ, Q is equal to KEQ, then the reaction's at equilibrium. Now this can get confusing because you'll notice that K and Q have the same form. You see this? But they can give you different values. So the way you keep these straight is to recognize that the only time you can use these values to calculate the equilibrium constant is if everything's at equilibrium. So this ratio only applies when the reactants and the products, and the products are at equilibrium. So we can only put equilibrium values into these concentrations when we're dealing with K. Q, in this form, we can put in any old thing, as long as it's, respective to this reaction. We can put the values of HI, H2, and I2, whether the reaction's at equilibrium or not. So keep that in mind. The values of the concentrations of the reactants and the products only at equilibrium apply when you're solving for the equilibrium constant, but you can put the values in at any time, whether you're at equilibrium or not, when you're calculating Q, the reaction quotient. Okay, let's try this problem, which relates to what we've been talking about. We're given this reaction where 2 moles of NO2 gas react reversibly to form N2O4 gas. It's given an equilibrium constant of 171 at 25 Celsius. If we're going to put 0.0015 moles of NO2, that's this gas, and 0.002 moles of N2O4, that's this gas, they're going to be placed together in a 10-liter flask. Is the system at equilibrium? And if not, which way will the reaction proceed? So let's write the equilibrium constant expression for this. We know that the equilibrium constant expression for this should be the concentration of N2O4 divided by the concentration of NO2 squared. And that should be equal to 171 if we're at equilibrium. So I'm going to put the subscripts down here. If we're at equilibrium, this should be true. Well, what is the concentration? Remember, the concentration is going to be our moles per liter. So let's see, my concentration of NO2, given the conditions initially in the flask, that's going to be 0.0015 moles over 10 liters. If we run the math on that, the concentration of NO2 that we're given is going to be 0.00015 molar. Likewise, the concentration of our N2O4 that we can calculate, that's going to be 0.002 moles in our 10-liter flask. And if we run the math there, we'll get a concentration of N2O4 that's 0.0002 molar. So we can use these values. These are the values of the molarity that are going to be in the 10-liter flask. Given all the information that we have, we can calculate Q. So to calculate Q, we're going to use the same form as the equilibrium constant. We're going to take our concentration of N2O4, which is 0.0002, and we're going to divide that by the concentration of NO2 that we're given, which is 0.00015, and of course we better square that. Well, let's find out where we're at. 0.0002, that's my numerator. We're going to divide that by 0.00015, then we'll divide that by 0.00015. So I've divided by that squared. We are at 8,888. So we see the value of Q is greater than K, and that's going to be able to tell me which way this reaction is going to go to get to this value, which is where this ratio should be for us to be at equilibrium. This value is too high, the numerator's too high, and this value is too low. So we want to decrease this value, which is going to shift us in this direction. And we want to increase this value, which will also shift us in this direction. That'll always be the case. It'll always be the case that both of these should be shifted in the same direction to get you to equilibrium. And so we see that because Q is greater than K, this particular reaction, in this setup, we are going to find the concentration of N2O4 is going to decrease, the concentration of NO2 is going to increase until we reach equilibrium, at which point this fraction will equal this value.